So black holes are really cool. And we looked last day at escape velocity, and I've decided on your test, just for giggles, we'll do escape velocity from a black hole. There are standard black holes, and then there are the supermassive black holes, like the ones at the center of most galaxies. Standard black hole is anywhere, it needs to have a mass of anywhere from about 10 to 100 times the mass of our sun. If they're bigger than that, something else forms. If they're smaller than that, I think they form neutron stars. But the way a black hole forms is you have a mass, a star, and it starts to collapse on itself. Now, at all times, it has gravity, and the gravity is causing it to want to collapse on itself because gravity is pulling inward. But at the same time, Lena, the energy involved in fission or fusion is pushing outwards, and so you have this equilibrium. But as material is being used up at the core of the star, eventually there comes a tipping point where the outward force of fusion is not as big as the inward pull of gravity. And the star will start to collapse on itself and become denser and denser and denser and denser and denser. And then it may form a black hole. So suppose you have a black hole that has a mass of 7.2 times 10 to the 31 kilograms. And suppose a spaceship is 9.6 times 10 to the 9th meters from the center of the black hole. So I've given you a radius. What's the gravitational field strength at this location? When I say gravitational field strength, what am I asking you to find? Sorry? I'm not asking you to find the force of gravity. Otherwise, I would have said find the gravitational force. And you're not the only one. Every class so far has made that same mistake. And don't get them mixed up. Gravitational force is F. It's measured in newtons. Gravitational field strength is not F and not measured in newtons. Redeem yourself, Nate. What symbol is it? Okay, little g. On your blue sheet, you've probably written this. I did not put that on your yellow sheet. I didn't put it on your yellow sheet on purpose. On your yellow sheet, you only have 3 equations. You have this one, Fg equals big G m1, don't write this down, m2 over r squared. Then you have the potential energy, the cosmic one, negative big G, big M, little m over r. But what's the third equation I put on your yellow sheet? And it's also on your blue sheet. What's the third equation that I gave you? Little g is defined as what? The force of gravity divided by a mass. If you go to the force of gravity equation, which I did give you, and you divide out a mass, you end up with universal gravity. I think that's a reasonable step for me to ask you to make, and so I deliberately did not give you that equation, Lena, on your yellow sheet. You can put it on the blue sheet if you want to. It's hidden on your yellow sheet. Combine the first and the third equations. Okay. I'm going to tell you right now the answer is not going to be 9.8. It's going to be 6.67 times 10 to the negative 11. 7.2 times 10 to the 31 divided by 9.6 times 10 to the 9th squared. What do you get? This may be in the hundreds, this may be in the thousands, could be even bigger. It depends how close we get to the black hole. And I was just making up numbers. I was trying to end up with something ballpark in the hundreds or in the thousands. Or what did I end up with? 52? Okay, that's okay. 52 point what?
0.1.
So 52.1 units. You could call this meters per second squared because you would accelerate at that rate. But when we're talking about gravitational field strength, because it's the force divided by the mass, which is also acceleration, you can also think of it as meters per kilogram. Could we survive that? Suppose we were astronauts in this spaceship. Could we survive? Or what if we had worked this out and instead of getting 52.1, supposing we had got 1052.1? Could we survive this? Matt, convince me. Suppose we found that the gravitational field strength wasn't 9.8 like on the Earth, wasn't even 52.1 like we just calculated. Supposing it was 1052.1. Could human astronauts survive that? You know what? Like a good physics question, the answer is both yes and no. Nate, is there gravity on the International Space Station? Yes. Do the astronauts float? So do they feel gravity? Why not? Because there's no which force? No normal force. So even though they're under the influence of gravity, do they feel the gravity? No. So if we were here and we were in a stable orbit, even if we were under the influence of this, would we feel it? No. So I think, at least on one level, I think we would survive. However, I said not 52.1, I said 1052.1. I have a feeling that gravitational field is big enough and would change fast enough that if you were floating vertically, there might very well be a difference in gravitational field on your toes versus your head because you're slightly further away from the black hole, and you could probably come to a point where that difference would be enough to physically tear you apart. Spaghettification? That's not quite what spaghettification means, but we're close. Okay? When you fall into a black hole, we call that spaghettification. We'll talk about that in a second as well. So let's suppose we were surviving, and Captain Nate says, okay, it's time for us to leave. What do we need for our escape velocity? I know you might remember the equation, but let's do the full derivation. How do we find escape velocity? Escape velocity says start with conservation of energy. And what do we want our final potential energy to be? We want this to be 0, and we want our final kinetic energy to be 0 because we want to come to a stop when we're free of the black hole. We want this to be just perfect. And so really, we have an equation where the entire right-hand side is 0. Kyle, what's kinetic energy been since day one? That V is going to be the V that we want to find. That's our escape velocity. Should be called escape speed, but they call it escape velocity. Okay. Plus, can I use MGH here, or are we cosmic? Yeah, we're very cosmic. Negative big G, big M, little m over R. Pause for a second. What would I do now? Yeah, I think I would get rid of that negative because there's a 0 there by plussing it over. And Lyndon, what I get now is a half m v squared equals positive big G, big M, little m over R. Not R squared, just over R. Now what? What cancels? Little m. And this gave us our expression for escape velocity. Spencer, what was the expression for escape velocity? You derive it from there? Get the v by itself. What am I going to do with the 1/2? That's times it by 2. Yeah, so it's going to be 2 big G, big M, little m over R, square root. Now, if you're lucky, if you still have this on your calculator, you might be able to just backspace, put a 2 in front of everything, delete the squared, square root. I'm kind of expecting this will be a bigger escape velocity than the Earth. I think the Earth was 11,100 and something. So let's crunch this just for giggles. 2 times 6.67 times 10 to the negative 11 times, what did I say the mass was? 7.2 times 10 to the 31 divided by, and how far are we? 9.6 times 10 to the 9th. Square root of that. I was hoping desperately I made up something that didn't require the speed of light. Because if we got an answer faster than light, we had passed beyond the black hole's event horizon and we were out of luck. That's a wonderful fluke. I was making up numbers this morning, and that's actually pretty nice. Bang on 1,000,000, just about. So 1.0 times 10 to the 1, 2, 3, 4, 5, 6. We could not do that with our current technology, but let's pretend since we're around a black hole, we've achieved Star Trek-ish technology. Black holes possess something called an event horizon. The event horizon is the point at which, going past that, light can't escape. And why can't light escape? Because the escape velocity is bigger than light. So C, at what radius from the center does the event horizon begin? We can use escape velocity, which we just rederived. V escape equals the square root of 2 big G big M over R. If I want to find where the event horizon begins, what is the escape velocity where that begins? Light. Who remembers from physics 11? What was the speed of light? So we're going to let V equals C was the symbol. It's on your formula sheet, I believe. I think the speed of light's on there, isn't it? 3 times 10 to the 8th?
Speed of light in the vacuum.
Yeah, it's there. Okay, so I'm going to replace that with that, but first, let's get the R by itself. What's the R inside? How to get rid of that? Both sides. So I'm going to go like this. Squared, squared, and I'm going to get, instead of V, I'm going to put the letter C, if you don't, the speed of light, equals 2 big G big M over R. And this is how you calculate a black hole's event horizon radius. How do I get the R by itself? Where is the R right now? Blech. Where do I want it to be? Oh, times the R over and divide the C. R equals 2 big G big M over C. 2, 6.67 times 10 to the negative 11. I forgot the, no. Oh, on the, you're right, there. Squared there, squared there. Wow, thank you. Who said that, Nate? Candy for you. Way to redeem yourself after your earlier force is field. Well, they both begin with F. Yeah. What was the mass? I think I have it on my calculator. 7.2 times 10 to 31. And it's going to be 3 times 10 to the 8th squared. Hey. I have a calculator that lets me go back more than one line, and I noticed 2 lines ago I have at least part of this typed. I have the 2, the 6.7 times 10 to the negative 11, and the 7 point. So I can just go 3 times 10 to the 8th squared and delete the rest. You get, holy smokes, Batman, that worked out evenly. 106,720? Yeah? I'll go 1.07. You know what? I'll write the whole thing because it worked out evenly, and how often does that happen?
Sweet.
In kilometers, if you were 107 kilometers from the center of this black hole, you're out of luck. Nothing in the universe can escape. Not only does this allow us to calculate the event horizon, this allows us to predict or calculate or figure out the mass of black holes. So if you know the radius, you know the mass of a black hole as well, so you can measure where the event horizon starts and get the big M by itself. If you ever wondered, how do we figure out how big what the mass of these black holes are? Right there. You figure out how far away the event horizon is from the central point that everything is orbiting around. Solve for M. It's doable. Suppose the sun began to collapse, and it maintained its mass, but its radius got smaller and smaller and smaller. At what radius will it become a black hole? And this is called the Schwarzschild radius. Okay. You know what? Lena, what's this asking me to find? R. What did we find right here? Turns out, if you can calculate the event horizon radius, the fancy name for that is the Schwarzschild radius. That's the radius beyond which, if a black hole is going to form, the star has to get smaller than that to create a gravitational field big enough that light can't escape, which means you can calculate what a star needs to do to become a black hole if you know the mass of the star. We have the mass of the sun. It's on our sheet.
Oh, yeah. It's 1.98 times 10 to the 30.
So I'm going to start out with our escape velocity little equation again. But again, we're going to let v equal c, the speed of light, because that's when all the good stuff happens. We're going to square both sides. This time Mr. Dewick isn't going to forget the squared. We're going to get c squared equals 2 big G, big M over R. We're going to get the R by itself, and I think, Linda, we get exactly the same equation as we just wrote. We get R equals 2 big G, big M over C squared. Caleb, what was the mass of the sun? 1.98?
Times 10 to the 30.
The sun is right on the fringe of possibly becoming a black hole. It's probably too small and never will, but let's suppose we had superpowers and could do this. What would we need to compress the radius of the sun to before it would stop emitting light? That's really what we're asking. It would go from being the brightest object in our sky to suddenly nothing. What do you get? You know what? I think, again, I can just backspace edit and just change some numbers. I got the 2. I got the 6.67. I need to change the 1.98 times 10 to the 30, and I should have just used my insert button. Oh, 1.98 times 10 to the 30 divided by 3 times 10 to the 8th squared. Delete, 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 delete. Is that right? Almost exactly 3 kilometers if you divide by 1,000, which is pretty staggering when you think how big the sun is. Okay, if we wanted it to become a black hole, how dense would we need to compress the matter? Well, from here to what? The library? That's probably about 3 kilometers-ish. Cram the sun into there. 2.93 times 10 to the 3rd meters. Black holes are cool. And I honestly, Eric, suddenly last night realized, oh, we did escape velocity. Of course, pick the escape velocity of the speed of light, and you can derive all sorts of neat stuff. I did a quick double check to make sure there wasn't some weirdness going on at those speeds with general relativity. As far as I can tell, nope. So we're good. So what am I going to ask you on your test? I guarantee there's going to be a question where I ask you how much work to put something in orbit. I guarantee there's going to be a question where I either give you one of altitude, radius, period, or orbital speed, and I ask you to find the other ones. In fact, you know what? How many fingers am I holding up?
4.
I'm probably going to make 4 versions of the test. I'll bet you one of them will give you the altitude, find the other 3. One of them will give you the period, find the other 3. One of them will give you the radius, find the other 3. One of them will give you whatever the last one, orbital speed, find the other 3. I don't know. I'm going to put you around a black hole, and I'm probably going to ask you to find the gravitational field strength and the escape velocity. And I'll give you more details on Monday. I think right now for you folks, let's pause the video for a second as I plan this out. Take a look at the take-home quiz, please. Quiz number 2. Every one of these questions is absolutely fair game for your test on the written section. So, number 1, I'm asking you to figure out how much work. Please notice that we're above the moon, because why wouldn't I go into outer space just for giggles? Screen's frozen, Mr. Dewick. Thank you. Number 1, I'm asking you to go into orbit in the moon. It is in an orbit. Did I say orbit? That means probably something. Okay. How much work to put this in orbit? Number 2, a satellite is placed into a stable orbit around the Earth at an orbital radius of 8.3 times 10 to the 7th. How much work is done in order to accomplish this? Mr. Dewick, didn't we do how much work to go in orbit in number 1? How come number 1 is 3 marks? Number 2 is 7 marks. Because in number 1, I gave you the orbital speed. I calculated it for you. In number 2, you're going to have to figure that out yourself. Number 3, planet Dewick has a mass of 3.14 times 10 to the 30th kilograms. Mr. Dewick? Yes, Nate. Does your planet have a mass of pi times 10 to the 30th? Of course it would. And a radius of 2.72 times 10 to the 7th meters. Mr. Dewick? What, Caleb? Does your planet have a radius of E? Maybe, because why wouldn't it? What's its escape velocity? Suppose an asteroid is traveling at 1.37 times 10 to the 4th at a distance of 2.2 times 10 to the 7th meters from the center of the Earth. If it impacts the Earth, how fast will it be traveling? So there will probably be an asteroid impact question on your test as well, or some kind of an impact question. Now, I can either ask you how fast it hits the ground, or I can tell you how fast it hits the ground and ask you to find R initial, where it started. Either or.